Good morning. Myself, Dr. M. Ravi, Professor, Department of Mechatronics Engineering, K.S.Rangasamy College of Technology, Tiruchendur. Today, we are going to see about system design and control. Frequency response analysis introduction. Frequency response. Frequency response is a steady state response of the system when the input to the system is sinusoidal signal. We already see the time response analysis. It is a steady state and a transient response. Here, the frequency response analysis is a steady state response system input to the sinusoidal signal. The merit of frequency response, the absolute and the relative stability of the closed loop system can be estimated from the knowledge of the open loop frequency response. Second, the practical testing of the system can be easily carried out with available sinusoidal signal generator and precise measurement of the equipments. The transfer function of the complicated system can be determined experimentally by frequency response test. The design and the parameter adjustment of the open loop system transfer function of a system from specified closed loop performance is carried out easily the frequency domain. The frequency response analysis and the design can be extended to certain nonlinear control system. The frequency response analysis can be used as a nonlinear system also. In time response analysis, it is only for linear control systems. Frequency response. The response of the system from the sinusoidal input is called as sinusoidal response. The ratio of sinusoidal response and the sinusoidal input is called as sinusoidal transfer function of the system. And in the general, it is denoted by T of J omega, where sinusoidal transfer function, the frequency domain response of the system, and it is called as frequency domain transfer function. The sinusoidal transfer function T of J omega can be obtained as shown below. First one, construct a physical model of a system using basic element or parameters. Determine the differential equation governing the system from the physical mode of the system. Take Laplace transform of the differential equation in order to convert S-domain equation. The domain determine the S-domain transfer function T of S, which is the ratio of S-domain output and input. Determine the frequency domain transfer function T of J omega by replacing S by J omega in the S-domain transfer function as a T of S. Note, if S-domain transfer function T of S is known, then frequency domain transfer function T of J omega can be obtained directly from T of S by replacing S by J omega. That is, T of S, S tends to J omega, that is equal to T of J omega. The frequency domain transfer function T of J omega is complex function of omega, hence it can be separated into magnitude function and phase function. Now magnitude and phase function will be real function of omega, then it is called frequency response. The frequency response can be evaluated for open loop system and a closed loop system. The frequency domain transfer function of open loop system and a closed loop system can be obtained from the S-domain transfer function by replacing S tends to J omega shown below. In open loop transfer function, G of S, S tends to J omega, G of J omega equal to modulus of G of J omega and angle of G of J omega. That is, the real function has modulus and the complex function has angle is G of J omega, angle of G of J omega. Open loop transfer function G of S into H of S rewritten as S tends to j omega, g of j omega into h of j omega is equal to modulus of g of j omega into h of j omega, angle of g of j omega into h of j omega. Closed loop transfer function m of s is written as m of j omega is equal to m of j omega m angle of m of where g of modulus of g of j omega, modulus of m of j omega, modulus of g of j omega into h of j omega are magnitude function. The angle of g of j omega, angle of m of j omega, angle of g of j omega into h of j omega are the phase function of the frequency response. Frequency domain specification. The performance characteristics of system in frequency domain are measured in terms of frequency domain specification. The requirement of the system to be designed are usually specified in terms of specifications. The frequency domain specifications are resonant peak MR, resonant frequency omega R, bandwidth omega B, cutoff rate, gain margin kg, and the phase margin gamma. The frequency domain's resonant peak MR, the maximum value of the magnitude of the closed loop transfer function is called as resonant peak, that is MR. A large resonant peak corresponds to a large overshoot of transient response. The frequency, resonant frequency, the frequency which resonant peak occurs is called resonant frequency. This is related to frequency of oscillation into the step response. Thus, it indicates of speed transient response. Next one is bandwidth. Bandwidth is the range of frequency for which normalized gain of the system is more than -3 decibels. The frequency at which gain is -3 decibel is called as cutoff frequency. The bandwidth is usually defined for closed loop system is transient signal whose frequency are less than the cutoff frequency. The bandwidth is a measure of the ability of feedback system to reproduce the input signal, noise rejection characteristics, and rise time. The large bandwidth corresponds to a small rise time or fast response. Cutoff rate. The slope of long magnitude curve near the cutoff frequency is called as cutoff rate. The cutoff rate indicates the ability of the system is the signal from the noise. Resonant peak, resonant frequency, gain margin. Next thing is gain margin. Gain margin Kg is defined as the value of gain to be added to the system in order to bring the system in stability. The gain margin Kg is given as the reciprocal of magnitude of the open loop transfer function at phase crossover frequency. The frequency at which the phase of open loop transfer function is 180 degree is called phase crossover frequency. Gain margin Kg is equal to 1 by G of J omega Pc. The gain margin Tp is expressed as Kg in decibel 20 log Kg, 20 log 1 by modulus of G of J omega Pc. The gain margin in decibel is given by the negative of the decibel magnitude J of J omega at gain phase crossover frequency. The gain margin indicates the additional gain that can be provided to the system without affecting the stability of the system. Next one is phase margin. Phase margin gamma is defined as the additional phase lag to be added at a gain crossover frequency in order to bring the system to verge in stability. The gain crossover frequency omega Gc is the frequency at which the magnitude of the open loop transfer function is unity, or it is the frequency at which the decibel magnitude is 0. The phase margin gamma is obtained by adding 180 degree of the phase angle by of open loop transfer function gain crossover frequency. Gamma is equal to 180 degree into pi of GC. Frequency response plots are Bode plate, polar plate, Nicholas plot, M and N circle, and Nicholas chart. The frequency response plot are used to determine the frequency domain specifications, to study the stability of the system, and to adjust the gain of the system to satisfy the desired specification. Next class, we see about the plots. Thank you for watching. Keep learning and growing.